Okay, so permutations is going to talk, I've started the video, so I'm just going to start. Permutations is going to talk about the fundamental counting principle. Okay, do you guys remember probability? Yes. Way back, so flipping a coin and landing on a head. 50-50, right? Like 1 out of 2, that sort of thing. Do you remember when you did 2 different events at the same time, like flipping a coin and rolling an even number on a die? Do you guys remember that? Well, you should have done it in like grade 8.
No, definitely not grade 8. We barely went through like trigger elements in grade 8.
Okay, so you guys know that the probability of flipping and getting ahead is 1/2. Because these are the total number of outcomes, and this is the desired outcomes. There's 2 sides to the coin. So what about the probability of rolling a 3? 1 in 6, because there's only 1 3 on the dice, but there's 6 sides to the dice, right? Everybody good with that? What's the probability that I'm going to get a flip ahead and roll a 3? Do you guys remember this? 1 in 12, yes. Because we take the probability of the head, getting the head, and times it by the probability of rolling the 3. So we should get 1 over 12. Okay, there you go. There is grade 8 probability. Okay? There you go. You didn't need to learn it. You got it here. So these are called independent events. So the reason why they're independent is they don't affect, like if I roll a 3, we don't scratch out the 3 on the dice. The 3 still stays. So the next time I roll, the same probability is for rolling a 3. Those are called independent events. So the reason why I'm talking about that is independent events. So if one event can occur independently, m different ways, a second can occur in n different ways. So what that would mean is we have 2 possibilities for flipping the head. And how many do we have for rolling the dice? So there would be 12 possible outcomes. And one of them we listed here. Okay? 12 possible. So does that make sense? So the fundamental counting principle is figuring out how many possibilities there are. Okay, here we go. License plate. License plate. What do we know about license plates? Assuming they're not vanity plates. Regular old Manitoba license plate. Okay, so I like to do my fundamental counting principles like this. These have to be letters. And these have to be numbers on a license plate. Okay, good. All right. Can you repeat letters and numbers on a license plate? Yeah, you can. My dad's license plate on his car was BBB040. Yeah. Oh, there you go. Okay. So how many possible letters do I have to choose from? 26. So if I pick the letter, let's say K, for my first one, of course I would. What? Kelly goes back, K goes back into the bin, so how many can I choose from next time? 26. And for the third one? 26. I don't think KKK is a great license plate. Not a good license plate. This is what, see, it all comes back to bite me in the butt. Okay. So, numbers. 10. No? Let's. Can we include 0? Okay, I'm just asking. So this one would be 10, and this one would be 10, right? So what do I do with all of those numbers? I multiply them all. I'm not doing that in my head. I'm going to my calculator and going 10 to the exponent 3 times 26 to the exponent through, oh. All right, so we have 17,576,000. So we have 17.5 million possible combinations. Now, I think that the Department of Motor Vehicles, which we don't have in Canada, that's a very American thing to say, MPI, Manitoba Public Insurance, there's probably combinations of letters that they don't release. Maybe like KKK, right? So we'll just go with generalities. We won't put any restrictions on it, but you get the idea that these things, right, that these things are probably reduced just because of practical reasons. Not nice. Okay, how would this question change if neither letters nor numbers could repeat? Nice. So I got my 6 blanks again. These have to be letters. These have to be numbers. I always like to put my restrictions underneath. So my first pick a letter is 26 letters. But if I've pulled the letter K out, now I only have 25. And if I pull the letter A out, now 24. I'm Kellyanne. Just FYI.
Is that your full name, Kellyanne?
Yeah.
Wow. Like,
Oh no, that's not like, it's Kelly, middle name Ann.
oh, it's not like Kellyanne, it's Kelly Hyperhat?
No, it's like Kelly, middle name we don't talk about, Ann, last name got from
Okay.
the paternal side. No, my mom's middle name is Ann. She's a Jocelyn. I don't know. There is no rhyme or reason to how North Americans name their children. So 11,232,000. Okay, so we good with that? Everybody good? I see that we've dissolved, guys. This is 5-pager of a lesson. Okay? All right. How many ways can a teacher seat 4 girls, 3 boys in a row of 7 if the boys must be seated at each end of the row?
Wait, say that again.
Okay, so these are my least favorite things to do. So how many seats do I have? 1, 2, 3, 4, 5, 6, 7. What's my restriction? No other restrictions, just boys have to be at either end. And for God only knows what reason.
So does it matter what order?
So what do I have here? How many possibilities do I have to choose from?
1,
No.
3,
How many boys do I have in the class?
3.
Just 3. So the first seat could go to any of the 3 boys. Then we go to our other B, because I've already put 1 in a seat.
Does that going to change the answer, though? Does it matter if the boys are at the end? Because even if they're not, the answer's not going to change.
It will start to change when we start blocking things off and doing things multiple different ways. Like, so Tripat and Basil have to sit together in a row of 10. How can they sit? How many different possible ways can they sit together? So, yes, you're right. It's not going to change this one. It will. It will. It will. How many boys do I have left? I'm just going to put, does it matter where they go? No, but I know they have to go somewhere. You're right. So now we have 5 people, right? Well, no, because it doesn't matter because we have 5 seats left. Everybody agree? We have 5 seats left? Okay, sorry, without that number 1. Okay, hold on, guys, hold on. I'm asking, okay, let me erase that because I'm doing 2 things at once. How many seats do I have left? 5, good job. Okay, we did this. This is awesome. So I have 5 remaining seats. Does it say anything about where they have to be? No. So how many people do I have left to sit? 5. So let's do this.
720.
Whoa, okay. That's going to change it. Okay.
Is it fine if I go 1, 2, 3, 4, 5?
Yep, for sure. But here's the thing: is we usually have to count down. There's a. So what I would suggest to you when you're dealing with these, deal with your restrictions first, like the position of where people have to sit, and then if I multiply all of these, that's going to be 720 possible ways or combinations. I don't want to call them combinations, but I did hear.
Are we needing to put open circles?
No, sorry, that just was me getting.
What else comes to be a better?
Yes, because there's a whole different lesson on. Yeah.
It's literally called combinations.
Let's go with that. I like ways. Okay, we good? Am I good to flip the page? Okay. All right. Okay. Hey, can we do the math and not talk about beverages for tomorrow?
We were talking about diseases that we could get from swimming.
Oh dear Lord. Okay. Either way, can we just go back to math?
Do you think it would be a good idea to swim tomorrow, given the weather?
No.
I think it is.
Okay. Hi. We're recording this, and it is 5 pages, and we have done 1. We're doing this. Whatever. I'm leaving without you guys. No, you're not. Feel alone. Feel alone here. Okay, so factorials, that exclamation point in math means something very, very specific. So it's a way to write these combinations a little bit faster. So if I have 4 exclamation point in math, it reads 4 factorial. And what that mathematically means is 4 times 3 times 2 times 1. So the factorial button, I'm going to flip back a page for a sec. So like when we were doing, well, these ones are a little bit different, but if I wanted to figure out what 5, 4, 3, 2, 1 is, I could have used the factorial button on my calculator to do that.
What is it?
Of 5, yeah. Okay, so let's grab our handy dandy calculators.
Find the second function for.
Let me grab a non-graphing calculator. I know where it is on my other one. Do you guys see an exclamation point anywhere? On mine? Oh, I do. Right there. Mine's right there. Yeah, it's gonna, so now we're gonna start using formulas with these in them. Okay? Okay, so I found mine. So what we're gonna do is you guys would agree that 4 times 3 times 2 times 1, what does that give you? 24. So let's check to see if in our calculator our factorial buttons are working. So I'm going to do 4 shift factorial. You must.
Are we going to get factorial graph?
No. No graphing.
I love that. Okay. There it is. Top the part. It is. Yeah.
Look above your number 4. Look above your number 4. So I put in 4 factorial and I got the answer of 24. Okay, so let's do 8 factorial is going to be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 40,320. Okay, so what's happening between each? So notice I've dropped the exclamation point. Like there's no exclamation point when I put it kind of in expanded form. I'll call it expanded form. Okay, I want you to do 0 factorial in your calculator. No. You just need to know that. Yeah.
You can do some funky things with 0 factorial.
Why?
Okay. All right, so let's do this one. No, I don't have a good explanation for you. I can research it and I'll tell you tomorrow.
Yeah.
I'll tell you tomorrow. I know. I'm super funny. All right, k plus 1 factorial. Okay, so it's going to be a never-ending thing. So when we did 8 factorial, what did we start with? 8. So what are we going to start this one with? K plus 1. So how did we get to the next term? We minus 1. So what's this one going to be? K. And what's the next term going to be? K minus 1.
That's me subtracting 1. I don't know what I can tell you.
What are you doing? Subtracting 1.
So we're using the factorial pattern and we're applying it to things that we don't actually know the value of. Yes.
What is it? Say that again, sorry? Mark, say that again? Oh, arithmetic.
There's no reason.
Is that like we did this before? But it was for adding. I don't remember what it was called.
So you have seen something like this in your infinite geometric series and sequences from grade 11. We're taking it deeper now. Okay? So again, I'll just review this one more time. Just like 8, when it says 8 factorial, we start with what it gave us. So if this gave us k plus 1, our first term is k plus 1. To get to your next term in the series, you're just subtracting 1. So k plus 1 minus 1 is k. And then k minus 1 is k minus 1. And then k minus 1 minus 1, k minus 2. We're not summing them, so we're not going to use a sigma. So a sigma implies that we're going to sum.
Not sigma. No, right side.
Okay, all right. So n has to be, so if this were n factorial, this is just it in general form, where n has to be greater than or equal to 1. Super exciting. Yeah.
Where do you take this?
Oh, it gets worse.
So why are we doing
Because it's, well, if you're going to do anything math-wise, you need to understand the binomial theorem, and you're going to see the counting principle show up multiple times. So if you're going to do any math course, whether it be stats or calc or linear functions or a logic course, these are coming at you.
When do you think it gets worse?
Oh, no. No, I'm just kidding. It's not terrible. When we had to do circles in the old curriculum, that was terrible. Well, where you had to sit around, like, so we're all sitting in a circle, and Basil and Trapat have to sit next to each other, but Kelly can't sit within 2 chairs of them, but we're all sitting in a circle that's infinite. It was bad, oh bad. Okay, this one. So we're going to use our knowledge of factorials to simplify.
What was that? E5.
So I'm just doing this one up here. Don't write that down, or maybe write that down. That's it in an expanded form. Would you multiply it through? and then divide, what would you start doing?
Cross out just 14.
Right? We'd just start doing that, right? But we can do it faster. So 5 factorial is the same thing as saying 5 times 4 factorial. Because what is this?
Oh, wow.
That's 4 factorial, right? So, what can I do now?
4 times 3. Oh no, you're gonna.
I'm just going to cancel them out because they're both factorials, and I can simplify them. Does that make sense to everybody?
There's a pattern here. You can keep going down until you get 0 with factorial plus 1. If you keep going following the pattern of doing this, that's the reason.
Okay. But I don't have a good explanation of it. Okay, let's talk about this one for a second. So I'm going to start. So I'm going to go 16, 15, 14, 13. Where am I going to stop? I'm going to stop at 12 factorial because my denominator has 12 factorial in it. So those will cancel each other out. Isn't that exciting?
It's like a non-calculator.
So this would be kind of like a non-calculator question. So 16 times 15 times 14. You guys, like, if you can make me multiply all these together, Skelly, and I'm leaving. So I don't, like, again, you could multiply them all together, multiply the denominators, and simplify those fractions. I'm going to do it right now. 3 goes into 15 5 times. 2 goes into 14 7 times. So really I'm going 16 times 5 times 7 times 13.
Whoa.
Oh, I guess this is 5. And then this one would equal, what's that? 16 times 5 times 7 times 13, 7,280.
I'm like,
Why can't we what?
like, does it matter? Like, should I cross out the 2 with the 16?
100% you could.
Okay, and it would just get the same.
Yeah, they were just stacked on top of each other, so I went with that. Yeah, you can totally do that. Okay, let's do n. So this is going to be, maybe I'll switch colors just because I feel like I'm getting crammed in here. N times n minus 1 times n minus 2 factorial over n minus 2 factorial. Those cancel each other out, and I'm left with n squared minus n.
Why does the O equal?
0 is.
So you only have an exclamation mark with n?
On the last one.
Why?
Because, like, so go back to this one. Let's go back to the smallest one here. So if I put it in expanded form, right, this thing that I circled here is the same thing as saying 4 factorial. So you could do it in fully expanded form if you wanted to, but when you've got numbers like 16, you would have 16 through 1 on your numerator, and that would be a lot of numbers to cross out. So you can stop. You don't have to finish your factorial. You can stop when it makes the most sense. All right. We good? You ready to go? All right. So this one, we've got numbers and we have expressions. 7 and then 6 factorial. And then this is going to be r plus 1, r minus 1 factorial. And that's over 6 factorial, r minus 1 factorial. So that's going to cancel out that. That's going to cancel out that. So I'm going to have 7r squared plus 7r. So we have to get comfortable using this fundamental counting principle with variables. But it follows the same principle as if it were numbers.
0 factorial is equal to 1 factorial over 1. Which gives you 1.
But that, why?
Because if you follow the pattern of decreasing, so you have like 2 is equal to 2 factor over 2.
I don't understand. I'm going to have to watch a video. Okay. How many different orders can someone play 4 CDs? This is important so that you know for tomorrow. Not that any of you are playing CDs, but just in case you might be. How many different combinations can we play 4 CDs? 4 factorial. Because your first option, you have 4 CDs to choose from. Your second option, you only have 3 CDs to choose from because you already picked one. Then you have 2, and then you have 1, which, if we're multiplying them together, that's 4 factorial, which is 24 ways. You're going to get really good at knowing some of the smaller factorials. And if you know what 4 factorial is, do you know what 5 factorial is? It's just 5 times this, right? I don't know. Just think about it. Okay, here we go. Permutations. This is where we are. Okay, so permutations. Permutations is an ordered set or sequence of all parts of a set. I don't know if that makes sense. So if I have letters A, B, and C, they can be arranged this many ways. And I want to say that order matters. What are you doing over there, Basil? Okay, all right. Well, that makes me a little sad that you're not as excited about this. Okay, this formula, ladies and gentlemen, is on your formula sheet, so you don't have to remember it. Okay. By the way, that's an N. It's hard to see, and that's an R. I know, but it's an N because the formula only has N's in it. N's and R's. Okay. So N is the total number of items that you have in your set. So rolling a dice, how many numbers do I have? 6. So N would be equal to 6. So N is your total. R is the special numbers you want to pick from your total.
So if you want, can you have multiple numbers?
Well, we could totally do that. Because which ones do you want to pick out of there?
Oh, but you do it individually though, right?
No. So in this situation, we have 9 in total, and we want to pick 4 items from it. So I have 9 students in the room, and I want to pick 4 of you. I don't know what 4. So I want to pick 4 of you out of 9. How many different possible combinations could I have? Now, N has to be a natural number. That's what the big N stands for. Sorry, I'm pointing at things you guys can't see. Little n is an element of the natural numbers. So what is a natural number?
1 to infinity.
It's a positive. 1 to infinity. Can't be 0. And can't be a decimal or a fraction.
So even negative though?
Nope.
Oh, only positive.
Only positive. So natural numbers are like the counting numbers. What can you hold in your hand? Like if you're thinking of like how many apples can you hold in your hand? Okay? Or how many little...
You can't have negative apples.
You're not holding 0 apples.
Yes.
You can't count 0 apples.
And you could technically cut it in half, but it's still 1.
It's still an apple, right? So we call it the counting numbers. Okay, so we're going to use this formula. Everybody with me? So 9, 4. FYI, your N always has to be bigger or equal to your R. I can't have 4 kids in the classroom and pick 9 of them, right? I say this out loud because some people get those confused, but that should be like something that makes you remember that the N is always your bigger number. Okay? So we're going to substitute that into the formula. So it's going to be 9 factorial over 9 minus 4 factorial. So we're going to have 9 factorial over 5 factorial. So 9, 8, 7, 6, 5 factorial.
Can we just put in our calculators like that?
Do we have to do that?
So what if I give this to you on a non-calculator portion?
Then we'll do it on our calculator portion, but this isn't that.
Have at her. What's your answer? You and your calculators.
So then you have
What
to
if you
do
get
this
given
with
a limit?
calculator, no?
Maybe if they weren't this big. What if these numbers weren't this big?
Yeah, I remember on 9, with 9 times 8 times 7 times 6 times 5.
Go old school.
Are you kidding?
You could work it out.
We're doing chapter 11.
Oh!
I'm recording.
You're rolling.
They're beautiful. I saw a picture of it. I'm so excited.
I know they're all downstairs.
I'm so excited. Did we set it up somewhere?
No, there's like some in the back and some like in the closet.
I just want to like put it up.
Yeah.
Do you think they'll let me?
Probably. You can do whatever
They,
you want.
true story. True story. I can.
Who's gonna tell you no, Miss Scallion?
It is a true story. I like it. It's me. Okay. I don't want to ruin it. I can't tell you. You'll have to wait.
Are we going to be, like, is it going to be...
I don't think you guys are gonna be as excited as I am about it.
Will it benefit us?
Yes, it will. No, you guys will all find out with everybody else.
When are we
Well,
going to
if you do it tomorrow, then no.
I'm going to tell you guys tomorrow.
Yeah, tell us tomorrow.
Okay, so we wanted a backdrop. Look, I'm telling the world now, it's on the video. We wanted a backdrop for you guys to be able to take pictures in front of. So what we did was we built a frame and we ordered like faux hedge greenery. So we have this huge 9x9 background, and we're going to decorate it with like beautiful red and white flowers and stuff like that. And so you guys will be able to be in your grad gowns and take that. And I did mention to prom that it could be used at prom too, because I thought it would look like, I think it would look,
At prom, that's really... Okay.
It's better enough.
okay. I'm so excited. I'm so excited. Okay, this is what happens when you let me arts and crafts for too long. Okay, so this is a situation where we don't know n. We don't know what n is. But we know it evaluates to 30. So we're going to use our formula. And so we know our numerator is n factorial. We know our denominator is n minus 2 factorial. And this all equals 30. So now we're going to go ahead and simplify. So we're going to have n times n minus 1 times n minus 2 factorial over n minus 2 factorial. So this would be a really good question on a non-calculator portion. Right? So we're going to n squared minus n equals 30. So n squared minus n equals a negative 30 equals 0. N minus 6. N plus 5 equals 0. So n equals 6. And n equals negative 5. What am I going to reject? Because n has to be a natural number. So we have to reject that. There you go. So this would be a really good question on a test quiz exam, on a non-calculator portion, and knowing how to, well, if we were going to, it'd be a great question. No, because I've left it to the last every time. I'm going to skip 3. You guys won't care. We're running out of time. Taylor and I just talked about this. Why does 3, 8 not make sense?
Because I have to...
You can't have 8 choices from 3 things. Right? N has to be greater than R.
Yes. Because you can do it. Just evaluate both of them, then you can see what they both are.
So N always has to be greater than, well, it could be equal to. It could be equal to. Sorry, I should put that in there. They can be equal, but you can't pick. So if I had 8 things and I wanted to pick 8 things, how many ways could I do that?
Oh, 60.
I have 8 students in the class, and I need to make a team of 8 students. I have 8 people to choose from, and I can only pick 8 of them. There's only going to be one combination. I got to take y'all, right? Like I gotta take y'all with me, right? Okay. I'm sorry. Okay.
That wasn't me. Don't lie to us. But I could have plus censored.
Okay. Permutations with repetitions in them. Where's Basil? Because I want him to understand how terrible this is. Okay. How many different combinations can I make? Hi, guys. Hi. Can I make with these 4 letters of 4-letter combinations? See, this is, so here's the thing. We have repeating, right? We have repeating letters. So normally it's 4 factorial, right? 4 letters, 4 factorial. But we have repetitions in this one. So it's going to be your total number divided by 1 set. And how many do I have in that set? 2 factorial. So what's the answer there? Quick.
Factorial.
No.
2.
No.
Factorial.
12. Thanks. Simplify it.
It's 12.
It's 12, right?
4 times 3.
4 times 3. 12. Okay. All right. So this is the thing. When you have repetitions, so you do your total factorials over however many repetitions you have. So let's talk about banana for a second. Banana. Banana. Okay? How many letters is in banana? Okay. How many repeating letters do I have?
5.
Yes, but how many sets do I have? 2. So I have repeating A's and I have repeating N's.
And one has 3 and one has 2.
So the A's have 3. So 3 factorial, 2 factorial. Because your A's have 3 different combinations and your N's have 2 different combinations. Okay? All right. Okay, good. Do the next one. Expand it. Okay. 6 times 5 times 4 times 3 factorial over 3 factorial, 2 factorial. So the 3 factorials are gone. So I've got 6 times 5 times 4 over 2 times 1. 2 goes into 6 3 times.
60.
3 times 5 is 15 times 4 is 60. So banana can be rearranged 60 different ways. You good? Okay, let's do the next one. Can you do the next one on your own? You can. What's 3 times 5? 15. What's 15 times 4? She got it? She's with, okay. Okay, next one. How many digits do I have? You can do it yourselves? Perfect. Because the 4s repeat and the 6 repeats.
30.
If you invite like two, how did you
Okay.
get so fast?
Well, Jacob's using his calculator or his brain. I'm not sure. Your brain?
I don't have a calculator right now.
5 times 4 times 3 times 2 factorial over 2 factorial, 2 factorial. So those 2 factorials, gonzo. So we have 5 times 4 times 3 over 2 times 1. Oh, that will definitely ruin things. So that, to me, is something you can do easily on a non-calculator portion. Okay, we're going to skip the path one. Too bad. Too bad.
Can you do that too?
No. Confused. No, but I would like to get through this constraints thing. So 5 people, A, B, C, D, and E, are seated on a bench. How many ways can they be arranged if E is seated in the middle? So E has to be seated in the middle. So I go back to my 5. 1, 2, 3, 4, 5. Yes, there is.
You moved it down. Well, 2.5. You have 5 spots. Oh, no. I need to go home.
Okay, how many E's do I have? 1. So E, I only have one choice in the middle. So sometimes it's easier to do with the dashes to put your restrictions in so you can see them. And then does it matter the rest of them? So how many letters do I have left over? 4. So it's going to be 4, 3, 2, 1. So how many ways? So even though I had 5 seats, which is normally 5 factorial, because that restriction was so specific, I had, that goes to 1, right? So it's 4 factorial. Okay, A and B must be seated together.
6.
Okay, so what happens?
Oh, that's terrible.
Hold on. A and B become a set. They are now treated like one person.
Wait, they only get one seat? Or
Treat them like they're getting one seat. But then we're going to come back to them in a second because there's something else we have to do. Okay? So then we'd have, so these guys sit in, it doesn't matter where A and B sit, but they have to sit together, right? So then we have C, D, and E. So how many is that? 4 possibilities. So that's your 4 factorial. But how many ways can A and B sit? 2. Because you're treating A and B as a pair, as one person. Okay? So they could sit either A first, then B, or they could sit B first, then A. So that is 2 factorial.
There's only different combinations.
So there's a restriction that 2 people have to be together. So you're going to start treating them like one person, and then you're going to go back and look at the set. So if 3 had to be together, let's say A, B, and C had to be together. So A, B, C must be together. How many people do I need to sit if A, B, C becomes one person? 3. How many do we have in total? 5. So ABC needs a seat, D needs a seat, and E needs a seat, right? So my seats are 3 factorial, but ABC can be arranged 3 factorial ways. So 3 seats for ABC, then plus D and E, and then 3 factorial comes from ways A, B, C can be arranged.
There's only one. No.
So they can only be arranged in 3 ways? That is a lot.
No, 3 times 3. So what's 3 factorial, guys?
I don't know.
Maybe 6, 12.
It's 6. So is this not 6?
Yeah.
And this is also 6? So how many ways can they be arranged? 36 ways.
Would it matter if you wrote like 2 factorial or 4 factorial for the first one?
No, it wouldn't because you're multiplying, so it wouldn't matter.
Are we getting the actual answer?
We can. This one was 36. And this one is, what's 4 factorial is 24. 24 times 2 is? Okay, A and B cannot be seated together. These guys are not our friends. The easiest way to do it is to take your total when it's no restrictions. So take your total. So no restrictions. Yep, that's your 5 factorial. Subtract the together. So we have 5 factorial minus 4 factorial 2 factorial. So 5 factorial is 120. This one we said was 48. So 72. So that's, okay, there's a different way to do it, and there's cases that we're going to do.
So before they were seen together, that's what the 4 and 2 factorial come, right?
Mm-hmm.
That's the total
Yep.
like ways they could possibly be together.
Yep.
And you're just subtracting it from the total.
Yep. Because in all other scenarios, they wouldn't be seated together.
Yes.
All right, Basil, you missed a significant portion. Okay, we've got lots of time to finish these last 2 examples, and these ones I like because it makes more sense to me to do it this way. Basil, you missed the most important parts. Yeah. I don't know, he left. Okay, let's, I want to add something in here. Numbers is too loosey-goosey, because then that would be rationals, that'd be everything. So how many natural numbers can you make less than 1,000 if repetitions of the digits is not allowed? So we're going to do cases. We're going to do different scenarios. And what's the first number that's less than 1,000, ladies and gentlemen? 999. So in case 1, we're going to deal with 3-digit numbers. Guess what case 2 is? Case 2 is going to be 2-digit numbers. And case 3? 1-digit numbers. It's just 9, not factorial. Just 9. Okay, anytime I do the lines, we're not using factorials because there's something really specific about them. Okay. Yep. Well, these are different cases. Anytime I draw the lines, I'm going to, well, I didn't put anything on the lines. This time we're going to put numbers in them. So these aren't factorials. So in 3-digit numbers, how many options do I have for my first digit? 9. Why 9? Can't be 0. Because if it's 0, then all of a sudden it's a 2-digit number, right? So not 0. So we have 9 possibilities. So we can't have repetitions. No. What gets put back in the second slot? 0 gets put back in.
Or it's 9 again.
It's 9 again.
Wouldn't it be?
You took 9 out and you added 0.
Because I've used one already in the first spot.
Oh, yeah.
Okay? But I used one and I put 0 back in. Because it's okay to be 204, right? It's not okay to be 24 in our 3-digit case. Yes, 8. Okay, what are those equal to?
81 times 8.
Okay,
Period, Amber. Okay.
648.
648. All I see are these people running in and out. Okay, 2 digits. 2 digits. What can the first line not be, or the first number not be?
0.
So not 0. So 9 and 9. Amber? She did the math already. I'm sorry, Danica. She had already done that math. And case 3. And why not 0? Because I said natural numbers. Okay? So,
This would be brutal if you had to do it.
oh, you will.
Oh. Jacob didn't even finish, and she was like, yeah, no, it's going to get
How? You'd have to use like a variable n.
I don't know what you're going to say, but I really just hate this unit, so I just think,
I love this. This is great.
Why did we add them and not multiply?
because they're not all happening at the same time. Like we're looking for how many numbers in total are less than 1,000. So we're not looking for a 3-digit number and a 2-digit number and a 1-digit number that are less than 1,000. We're just looking for the total number. So this is why these aren't multiplied. You only multiply when you're looking for things to happen at the same time.
So,
Probability.
So this is like
I'll rewatch the video.
So like this is
Okay.
so this set
Okay.
of numbers.
All right. Let's move on. We don't have much time. We got 5 minutes left. I'd like to get this last one in so you go off tomorrow and come back for exam review tomorrow with all this knowledge in your head. Okay. How many different 3-digit even natural numbers greater than 300 can you make using the digits 1, 2, 3, 4, 5, and 6? No repetitions allowed. Okay. Okay, so case 1, they have to be even. They have to be 3-digit. Oh, sorry. And they have to be greater than 300.
So it's an even.
No.
Three.
So they. Okay, so there's your first case. There's your first case.
So 4, 6, and 8 are the only ones for the first.
Okay, there's no 8, but I'm with you.
Wait, why is there no 8?
I don't know. The digits are listed there.
Oh, I'm not reading. Okay.
Okay.
Hard question.
All right, so we can put 3, 4, 5, or 6, but remember that they have to be even. So what does the ending number have to be?
2, 4, 6.
Okay, but I've put 4 and 6 here. So what has to be here? 2. How many 2s do I have? 1. Good job, everybody. Yeah, we're going to do that for the other cases, Danica. We're going to do that for the other cases. You're just jumping ahead. So we have 4 options here. And then what for my next line? So I've used 1 here and 1 here. So how many remaining do I have? I have 4. Okay, guys. This isn't something that you can kind of pop in and out of while we're explaining it. So let's run through this again. Am I putting all 4 numbers on this line? No. How many am I picking? I'm just picking 1, but I have 4 possibilities to pick from. So if I have 1 number here and 1 number here, that means I have 4 left. Okay, everybody with me? So that's 16. Okay, so case number 2. So we're going to end, this one ends in 2. This one's going to end in 4. So if this one ends in 4, what can go here? 3, 5, 6. So there's 3 on this line. And if I use a digit here and a digit here, how many are left? 4. So guess what our last case is? It's going to end in 6. So I only have 1 of those. So what can go on this line? And what do we do with our cases? Add them. 24 plus 16?
30, 40.
We survived. I only skipped 2 examples, and I think you'll live a full and happy life without them.
This is like computer science.